Hello friends, this is Pawan Sai Tadepalli. You are watching Eureka Learning channel. So welcome to the Eureka Learning's YouTube channel friends. Today I come up with a new video. This video about the data science project friends. So in this video I am doing one project. So you will get very good information friends. So this project is very interesting as for the beginners or the intermediate levels. In this video, I am doing project called Concrete Strength Prediction, friends. Why I choose this project? Because concrete is one of the most important materials. So knowing the compressive strength of concrete is very important when constructing a building or a bridge or anything. So the compressive strength of concrete is highly non-linear function, friends. So uh, this property gave interest to me to predict the strength. We can predict because we have, machine learning. There are different types of algorithms to tackle this type of nonlinear functions. So I choose this project, friends. So this is the main motto behind this project. Oh, concrete is a highly nonlinear function, as I said, because there are different ingredients used in making it concrete. So I am predicting the strength. If I change with any ingredients, the values of ingredients, then what will be the strength? The strength will be increase or decrease. So I want to know. So for this reason, I'm doing this project. So this notebook demonstrates the use of machine learning to predict the concrete compressive strength, friends. So my problem statement is predicting compressive strength of concrete given its age and quantitative measurements of ingredients. So these are the important libraries to implement this project. So I am importing NumPy, Seaborn, Matplotlib for visualization purpose. I am importing Pandas for data analysis and data related tasks. For model building. So this project I am doing with only linear models, friends. I am comparing the different types of linear models in the scikit-learn. So which model to know which model is performing better, which model is not performing better. So I am doing normalization for, so I am taking standard scalar, friends. So as I already said, I am implementing this project using only linear models. So I implemented linear models like linear regression, lasso regression, and ridge regression, friends. So these are the regression type. This is a regression type problem. So I am implementing this regression matrix like mean squared error, mean absolute error, and R2 score. Why I import R2 score? Because I am using only linear models now. That's why I'm importing these models. This model, this decision tree and random forest are not related to this video. So I upload to another video, friends. This two will be useful for that video. So I am ignoring the video. So that's why I'm importing the warnings. I am filtering the warnings called user warning, runtime warning, future warning, and depreciation warning, friends. If you want to filter these warnings, you can do this, or otherwise there is no necessity to run this code. So I am setting the number of rows and columns, friends. For normal purpose, I am using this. So I am printing 1 lakh rows and 1000 columns. So this is the presetting while I am doing, this is my presetting while I am doing my any project. So I am doing this project in Google Collaborate reference. So my data set is present in my drive, Google Drive. So first to get my data set, I am accessing the drive using this command from google.collab import drive, and I am mounting my drive to this collaboratory. So I like this command like drive.mount, and so you need to access Google Drive. You should write a command like this G drive. After running this command, so one link will be present on this output. So you have to click on this link, and after it asks allow this your drive. After allowing your drive, they will provide one security link, friends. Please copy that link and paste it here. Then after some time, it will be show like mounted at your Google Drive. So this is about accessing Google Drive, friends. So now I am reading my data, friends. So getting the data. So this data is in Excel file. So I am using this command pd.read underscore Excel, friends. I will upload this data in the description part in the video, friends. Please see the description. So data is equal to, I am reading this data. So in this, I am printing the only top 5 rows of data. Means data.head. Defaultly, it prints only top 5 observations. So these are the features, friends. Cement, all are in kgs. Cement and blast furnace slag and fly ash, water content, superplasticizer, coarse aggregate, fine aggregate agent, concrete compressed ocean. This is our output. This is our dependent variable, friends. On these remaining are the independent variables. So I am printing the total number of observations. So for that I use this command length of data. So it gives 1030. So it means it indicates there are total 1030 observations are there in this data set. So because these feature names like this feature names are like very big, friends. So these feature names are very big. So I am changing these feature names, friends, using like this requiring column names, requesting column names, friends. So I shortcut like this: cement, blast furnace, slag. So I am removing this, friends, kg in a meter cube mixture and component. I am only this top lines: cement, blast furnace, slag, fly ash. And these are the current column names I am printing. I am this in list to data type. So after I'm using mapper function for I common name in enumerate. Enumerate means it gives to enlarge the which variable we give. So it give that number and the name. So I'm using this mapper. I am taking this mapper as it. So empty taken and I am mapper of name. So I am assigning this new column names. So after I am renaming the column names, friends. So after renaming the columns, I am printing this data top 5 because this is a dictionary format, friends, because I use mapper function now. So there will be q value function. That's why I take this dictionary type. So I am printing this data, friends, only top 5 observations, and I am printing the total data type, like how many columns are there, how many observations are there. There are 9 columns, means 9 features, and each feature has 1030 observations, friends. So coming to data cleaning, I am checking the null values. Is there any null values are there? So there is no null values, friends. So there are no null values in the data. Why I am writing this after running the code? Because this is the storytelling of notebook, friends. After some days you open this notebook, you don't know because we forget. Normally you are humans, we forget about this. If you write like this about this uh, each line, you will get a very spontaneous idea about this. So that's why I write like this. This is called storytelling of notebooks. So if you share this notebook to anyone, they will understand easily. So please note this point, friends. So I am printing about the data. So data.info means it gives the type of feature, the data type of feature. Is there any null values and total number of observations, how much memory it is consuming. So there are no null values, friends. Only age is the integer data type, remaining are floating points, friends, including our dependent variable. So the data set is 72.5 KB, friends. So let's start the EDA part, exploratory data analysis part, friends. First, I am exploring the data. So I'm going for descriptive statistics to know about the data frames. So to know the descriptive statistics of data, so you need to use this command data dot describe dot describe. This method gives a mean 25% or the, like that values and standard deviation of values, maximum value, and the transpose. Because normally these features will come under this in the upper part, and these descriptive statics come under this in this part. So after transporting, they will change. So we know each feature. So there are 1030. All feature have same number of observations. From this also we can say there are no null values under the cement. So the average kgs using this cement is 281 kgs frames, and the water averaging they are using 181 kgs, and average age of cement is 45 days frames. See, you can see the age 5. So they mention days. So average age of cement is 45 frames, and the average strength of is 35. So this is about the descriptive statistics of the data set frames. So I am finding any relations. Is there any like with one feature related to another feature? This is called multivariate analysis, friends. So I am doing next step. My next step is multivariate analysis. To do this multivariate analysis, we have some Seaborn library. This is very helpful library, friends. So in this Seaborn library, if you want to do multivariate analysis, use this method, pair plot, and give your data. And after this plot dot show, you need to write like that. So it give all the relations you come with one feature to another feature, friends. See, the data is very irregular and there is no only relationships. There is no linear relationships. As I already said, this is a non-linear data, friends. As I said, this is like data is look like that only. So only some has linear relationships, friends. See, only cement and concrete strength has a linear relationship. The cement is more and the strength will be more. So from this graph, I didn't observe anything. Only those feature, friends. To know about more about the relationships, I am going for correlation part. For finding correlation, I am using Pearson correlation, friends. So if you want to use Pearson correlation, if you want to find Pearson correlation, use data.core. Defaultly find the Pearson correlation to you. So after I am printing I am drawing the figure of each feature correlation values, friends, using heat map. I'm annotating the each value, friends. So this is about, see, I will note down the observations also. These are my observations. There are not any high correlations between compressed strength and other features, as I already said. Because see, friends, there is no, all values are very small. So except for cement, so strength, cement and compressive strength will be high, as I said. Age and superplasticizer are the two other features which are strongly correlated with compressive strength, friends. So, friends, superplasticizer, age, compare, see, friends, age and superplasticizer. So, age and superplasticizer are the two other which are strongly correlated with compressive strength. See, friends, age 0.33, okay, not bad. And super plasticizer, friends, very super. See, 0.37 is compared to more than age, friends. Remaining are all less. Because this is our dependent variable now, friends. Only cement is more, and water also less, fly ash also less, this also less. But age and super plasticizer are more. Have relationship. So, superplasticizer. Another observation is superplasticizer seem to have a negative high correlation with water, friends. So let's see water and superplasticizer. See, friends. So these are my observations, friends. I normally like these observations. You can find any and you can write remaining points also. So superplasticizer is as with the negative values. Scores aggregate also negative value, water also negative value, friends. So these are all my observation, friends. So we can further analyze these correlations visually by plotting these relations, friends, using distribution plot, using SNS Seaborn library. So I am printing all the features. So these are the features, and I am printing the distribution plot for know the distribution of each feature. So this is the our dependent variable, friends. So this is the distribution of the our dependent variable, and this is the y-axis. I take density, and x-axis I take a compressive strength, cement strength, concrete strength, friends. So this is multivariate analysis, friends. Now I am coming to univariate analysis for simply our understanding purpose. For if you want to do univariate purpose analysis, we have probability density functions, cumulative density functions, box plots, violin plots, distribution plots. But I don't use some other methods. I am using only this method, friends. So PDF. So after first I am going, you need to know bin underscore edges and counts, because for PDF calculation of PDF and code CDF cumulative density function, we need to know count, friends. So how can we get the count, friends? By using histogram method using NumPy library. So I am calculating these two values. So using np.histogram of data of our dependent variable, I am only taking 10 bins for histogram, and I'm printing the values, friends. So see, so these are the values. First I'm printing the counts. These are the count values, and this is the PDF, and these are the bin underscore edges, friends. So this is the how PDF is look like. PDF is look like density function. So when the strength is increases, the values are decreases. See, you can observe this. So this is the how distribution changes. And cumulative. Normally in the name itself, cumulative means it is a series of adding. So I am adding these density functions. How this CDF will always be increasing manner, friends, because we are adding in the series one by one. No? So now I am combining this PDF and CDF to better understanding. So same, friends. Same, first I am printing PDF, and second I am printing CDF. So to calculate the PDF, we know the counts, and so this is the formula, friends. Total how many counts by sum of counts. So you will get PDF, friends. So this is the PDF. Blue color is the PDF, friends. And now I am calculating the cumulative density function. So it will increase. So to calculate the cumulative density function, so there is a method called CumSum in NumPy library. So for this, I'm taking PDF, because from density of PDF only we get the CDF. So this is always be in increasing manner. These are the PDF and CDF values. So there will be no much difference, friends. Only small difference between PDF and CDF. For understanding purposes only, I take these two. So if you draw a line in from 70 to this one, so they will intersect, friends. So what it says, so if you draw a slide from concrete strength value at 70, so then it intersects the curve at 0.9 maybe. Value approximately zero point 0.8. So that is there are total 80% from strength from this from 30 to this 80 observations, 70 observations, friends. So this is the observation. After I am finding the relationships for our dependent variable with another variables using only scatter plot, friends. Before I am doing pair plot now, so we can know about all the observations. But if you want to analyze more features with dependent only one dependent variable, so scatter plot Seaborn will be very useful. So in the Seaborn, we need to write like this for scatter plot, SNS dot scatter plot of, we need to give x and y variables. For y is the our predicted dependent variable concrete strength, and X is the I am taking a cement. So, and I am adding these two features also because I want to know the relation. If the water is on edge or more or less, what will be the strength? The so these are normally we know for the cement, these three, water and edge, and for concrete, these three are the important features. First, so I first taken this feature, friends. Data means data, and axis, AX is the axis, and this is the figure size, friends. I am putting title and legend. So for legend, I am taking only 1,1 dimensions, friends. So see, friends, what I observed is compressive strength increases with the amount of cement. So, cement, see friends, this is the less value and this is the more value. So, if the value is increasing, the strength is increasing, friends. You can observe because there is no values in this. If only at 100 to 300, we have only some values because it means the strength is decreased if the cement is low. If the cement is high, if the cement in kgs is high, the strength is increasing, friends. And coming to water, see, if the water is more, it indicates with this color, black color, friends. See, the water also more. This also the black color indicates the water, friends. Coming to age, if the age is more, the strength also more. So, see from this, if the water and age is more, the strength is increasing. See, cement compressive strength increases with age. As I already said, the age is more, the strength is more. The water is more, the strength is more, friends. But not like that. If the water is less, the strength is good. Normally, from these observations, the water is less, the strength is good, friends. Please observe this. But if the age is more, the strength is more. But if the water is less, the strength is more, friends. See. These are the observations. Compressive strength increases with the amount of cement. Compressive strength increases with age. And cement with the low age requires more cement. Cement with the low age means, so these are the low age means, so it gives more, the strength is less, so we need more cement. And if the age is more, means the water content required also more for the better strength. So these are the observations, friends. And for I want to analyze remaining features for dependent variable like fine aggregate, fly ash, and super plasticizer, friends. So only this parameter, this x and y will be changed, remaining will be same, friends. So see, with the, as fly ash increases, the strength will be decreases automatically. So see, friends, 200 means black color, means the strength is less. See, friends, look small dots, so it gives strength is less. There is no black colors in the upper part, mean the strength, if the fly ash content is less, the strength is more. If the fly ash content is more, the strength is less. So we need to observe the super plasticizer. The super plasticizer is more, we need to see. So strength, compressive strength increases with the super plasticizer. So if because the black color values are increasing, the strength also increasing, friends. See, black color dots because big dots. So small dots require fly ash and big dots indicate super plasticizer, but not much strength, but there is a relationship between, friends. So this is the observations with fly ash and super plasticizer, friends. And there are so many other features. So I take that feature, fine aggregate, water, and super plasticizer. So coming to this, so friends, black color. So where is the black color? I mean, these are all the black color, friends, small dots. So from this we can know if the water is more, the strength is less. The water is more, the strength is less. And the water is less, the strength is more. See friends, like brown, like brown. If the superplasticizer also more, the strength also more. We know already. See, strength decreases with increase in water, strength increases with increase in superplasticizer, as I already said. So fine aggregate. Coming to fine aggregate, friends, the fine aggregate is more fine aggregate is used when less water, more superplasticizer is used. Friends, fine aggregate is less when we are taking, so we are taking less fine aggregate when the more water, friends. This is the observation. So this is my conclusion, friends. So we can visually understand 2D, 3D up to maximum 4D plus planes. Other than that, 4D means we can differentiate with colors. So this is also we can observe important feature like relations using Pearson, pair plot, and scatter plot, friends. So this is normally analysis part, but machine learning will do this analysis also. It will give which features will be useful for prediction the strength. So that one, I am next. My steps is being building the model frames. For that one, I have to process data before to giving to my model. So the next step is data processing. So first step is I am separating the dependent and independent features. Input features are the independent features, non-target variable is a dependent feature. So x only last variable is our dependent variable now. So I take it, I give it to a y variable, remaining are x variable, friends. So for I am splitting the data to reducing the overfitting, friends, and bias. So I am into I take 80 20 percentage. So I am taking 80 and 20%, friends. After I am scaling, because see, if you go to the data set, friends, one feature will be have one scale and another feature has one scale, friends. See, these are in hundreds. This is look like more. So that's why if you fit to this data set directly, so the coefficients will increases because these are the linear models. No, they fit coefficients. So if you don't normalize this data set, the coefficients will be more. So which the value of range is more. So the model may give wrong predictions. That's why I'm normalizing the data using standard scalar frames. 1 minute, I will show scaling. I'm using standard scalar. I'm fitting the data. So the scalar is fitting on the train data and not the testing data, because I am fitting only on train data, because after we give model to only training data, after testing data we predict now so we don't need to fit. So but we need to do transformation. If you don't do transformation, the model may give wrong results because the variance and standard deviation will be different if you don't do scaling and after scaling. So our next step is model building, friends. I am using only linear models. So in the linear models, there are three types: linear regression, no regulation, lasso regression, and one regulation. It means try to push coefficients to zero, and ridge regression, L2 regulation. So tries to keep coefficients as low as possible. So we will compare these three algorithms, friends. So first I am importing these three algorithms and giving assign to this variable cell or lasso and ridge. So after I'm fitting the every model, I'm fitting. So I am fitting linear regression model to train data and lasso regression and ridge regression also, friends. So these are the parameters in that models. So I am predicting my predictions with the test data, friends. So I am predicting with the linear regression, lasso and ridge regression. After predicting, we need to evaluate how these models are performing. So for this performance, we have some metrics. These are all that metrics: would RMSE, MSC, MAE, and R2 score. So I am predicting these all metrics values, friends. So I'm which model I take. Model and printing like slash t means tab. How much space you need to give for each metric. For this one, model is very linear regression is very big center word now funds. That's why I take only one t one space. For model, I take three. Now, if you want more, you can take more. So I want two decimal points of I want two decimals. So I take dot to f friends. So these are the values for MSc, MS, and MAE for a linear regression. For the same for lasso and for the same for ridge friends. After I'm combining these three, so I'm printing this table like so. These are so it seems look all are giving same results, friends. Only whole less very minute difference. See, the performance seem to be similar with all the three models. So these are the linear models now, friends. These give coefficients. So I am printing all the coefficients with the different models like linear regression coefficients, last one ridge regression coefficients. So I am taking labels because I am printing for each label how it give coefficients. So labels means so we know label is our last column. So I'm printing that layer, giving these two labels and x. Why I take this x because I will tell friends and width. So I want to draw like this, friends. I want to draw bar plots. So I want to draw bar plots for these three models, and I am annotating the each coefficients for each feature, friends. That's why I take three bar plots for because we have three models now, friends. So first, like I take variable plot or subplots and only one plot now, friends. So there is no need to give a number in the plot dot subplots method. We need to give only figure size. And so I am using box bar plot. So x dot bar. So x dot bar has I will tell friends about x dot bar, friends. It has some parameters like x, height, and width on bottom and align equal to center. Width the default is 0.8, friends. If you want to change that width, you can change. So for this, I have width. I give bar plot width is a 0.3, friends. And height we have to give and x. So x is the so I will tell about each parameter, friends. X is the coordinates. The coordinates, friends. Height of the bar, width of the bar. So we have to give bar plot coordinates now, friends. So I am printing the labels. So every label, length of labels. So how many labels I am giving from this is a sequence of scalars because these are only integers now, friends. It means scalar. So it is x is a sequence of scalar. So I am giving x because I have to draw this for three models. So left, center, and right, friends. Assume like that. For left, that one I am giving -2 into width by 2. So this will give left part, friends. And coefficient underscore lending rate is the so we have to give height now, friends. That is the coefficient underscore lending rate. So up to which height your ball should be like. So I am giving coefficient underscore lending rate as a height. For width, I'm giving the same 0.3 and label if you want to give any label can give. For center part, I am not adding or subtracting. I directly give coordinates and height as a giving in the middle part. I am drawing the lasso regression coefficient, friends. So I am giving a coefficient underscore lasso as a height parameter and width will be same. For ridge regression, it should come under the right part. So I am adding to middle part, friends, for x. And these are the labels. After each bar plot, we know coefficient. So that's why I'm annotating the bar plot, friends, with the coefficients. So see, friend, this is a very useful function, auto labeling. So for rect in rects, friends. So rect means which part for which bar graphs we have to annotate. We have to give like that. So height, we have to know height now, friends. So I am taking get underscore height, friends, this rect. So rect means so bar plot give this height. And after we have to annotate, I have to annotate with after 2 decimal points, friends. That's why I take. So these are the parameters like B. for the x dot annotate s comma xy. So yes, the text of annotation. Which text you want to annotate? Like we have to annotate our coefficient of friends. This is the text. So I have to give this height means the coefficients values friends. So this is the text and xy means the coordinates. The point, the x comma y to annotate. Where we have to annotate? We need to know coordinates, the friends. And there are xy test means the position x comma y to place the text coordinates. It is the bar coordinate friends, and this is how the bar should be, center or bottom. So if the values also given in the there are will be negative values now friends. In that case we have bar should be in the negative part, so that's why I give this bottom. So and after I am fitting this function friends for each bar plot, and I am using it. So after I have writing this line called figure dot height underscore it out. This method fits the all values too tightly, and after we have to give plot dot show, and this is the graph friends. So for this each feature, so this blue indicates linear regression, orange indicates lasso, and for ridge it indicates green friends. For each feature, what are the coefficients? So the linear regression and ridge regression will be same friends. All the cases it gives only so many, only less point difference, but it looks similar. But only lasso is the giving very coefficient less coefficients, because I as I already said at the time of model building. So lasso tries to push the coefficients to zero and ridge regression as low as possible, because it gives directly a zero results now, so it gives very less coefficient friends for each feature. These are the coefficients. So from this, I as already said, my observation is the lasso regression reduces the complexity of model by keeping the coefficient as low as possible. Because if the coefficient values are more, the model is complex because it will overfit to only that features. Coefficient with the linear and ridge regression are all the same, as I already said, friends. I am plotting the predictions to better understanding purposes. So these are three models now friends. We have to take three pictures, three images, like three plots, x1, x2, x3, and plot or subplot, because we want plots. So I give three figure size. This is the figure size first plot. So which is the first plot? Linear regression, as I take first plot. So I am drawing uh, x dot one dot scatter for relationships, how uh, this linear model fits the data. So I take so we need to give x and y values. So y predict on predicting values and texting values, and this is the size of the points. And so we need to give coordinates of the plot, x and y coordinate. This is the x and from min to max, and for y also min to max range. And this is to how the your line look like I take a dotted line friends, and line width is 3. So and x label as true and y label as a predict, and linear regression for lasso ridge will be the same. So this is the friends. So looking, so friends, linear regression fits correctly. Allah looks fits correctly, friends. But see, what I observed is regard to values of the target, we can conclude that linear and ridge regression are well, because all there is, compared to lasso regression, the distance is less, friends. See at this part, if you do this part, it has more distance compared to this, because see, so from my observed, what I observed is linear and ridge performed better for this data, and lasso is not performed better. But lasso regression reduces the complexity of the model. So this is all of my observations, friends. So this is about the concrete strength prediction with the linear models, friends. So please subscribe my channel, friends. I hope I like this. You like this video. So please share to your friends, and please subscribe my channel. And thanks for watching this video. If you like this video, please put a like button and give a comment, friends. Thank you so much, friends, watching this video.